Good evening everyone. I welcome you all to the week 12 live problem solving sessions in mathematics algorithms and applications course. So this will be the last lecture of a live problem solving session. So tomorrow we'll be taking one more session for recap. So in these lectures, I would like to provide introduction to machine learning, which we started in the last class, followed by that introduction to wake up workbench, and also how to uh, develop different machine learning tasks and also validate those machine learning tasks. Machine learning is based on the idea that computers can learn from data, identify patterns on their own without being explicitly programmed. It involves developing algorithms that can automatically improve their performance on a specific task by learning from examples or data. In traditional programming, a programmer writes a code that tells the computer exactly what to do for a specific task. However, in machine learning, the computer learns to perform a task by analyzing and learning from the large amounts of data. The machine learning algorithm can then use this learning to make predictions or decisions on new data. The process of machine learning involves feeding large amounts of data into an algorithm and allowing the algorithm to learn from that data. The algorithm looks for patterns and relationships in the data that are relevant to the task at hand. Once the algorithm has learned from the data, it can then be used to make predictions or decisions on new data. For example, in image recognition, a machine learning algorithm can be trained on a large dataset of images labeled with different categories such as cats or dogs, and the algorithm learns to identify the features and patterns that distinguish cats from dogs. Once the algorithm has learned from this data, it can then be used to identify whether a new image contains a cat or a dog. In summary, machine learning is a powerful tool that enables computers to learn from data and make predictions or decisions based on that learning. It has many applications in areas such as natural language processing, image recognition, speech recognition, autonomous vehicles, and other things. So in this, I'll be talking about classification of machine learning. There are three main types of machine learning. So one is supervised learning. In supervised learning, the algorithm is trained on a labeled data, which means the data has a known output or a target variable. The algorithm learns to predict the output for a new input data based on the patterns it learned during the training. Next one is unsupervised learning. In unsupervised learning, the algorithm is trained on unlabeled data, which means that the data has no output or target variable. The algorithm learns to find patterns and relationships in data, such as clustering and dimensional reduction. Third one is reinforcement learning. In reinforcement learning, the algorithm learns to make decisions by interacting with an environment and receiving feedback in the form of rewards or punishments. The algorithm learns to maximize the cumulative reward over time by taking actions that lead to positive outcomes. So machine learning has wide range of applications across various industries, including healthcare, finance, marketing, manufacturing, transportation, natural language processing. So machine learning is used for disease diagnosis and prediction, drug discovery, and personalized treatment plans. Machine learning is also used for fraud detection, risk assessment, and portfolio management. The process of machine learning can be broken down into several key steps, which are as listed here. The first step in machine learning process is to collect and pre-process the data. So this involves identifying the data sources, collecting the data, cleaning and transforming the data. Then splitting this data into training, validation, and testing set. Data pre-processing also involves feature extraction and feature engineering, which involves selecting and transforming relevant features in data that will be used by the machine learning algorithm. The next step is to select an appropriate machine learning algorithm that is best suited for the task at hand. There are many types of machine learning algorithms, including supervised, unsupervised, and reinforced. That's what we have discussed in the last slide. And the choice of algorithm depends on the type of problem being solved and the type and size of the data and the desired output. Once an appropriate algorithm is chosen, the next step is to train the model using training data. During training, the algorithm learns to identify patterns and relationships in the data that are relevant to the problem being solved. The performance of the model is evaluated on the validation set to ensure that the model is generalizing well to the new data. After the model is trained and it is evaluated on the test set versus its performance. If the model is not performing well, then it may be need to be fine-tuned by adjusting its parameters or by changing the algorithm. Once the model is trained and evaluated, it can be used to make predictions or decisions on new data. The output of the model can be in the form of classification, where the model predicts the class of an input, or a regression, where the model predicts a continuous value. Finally, it is important to monitor the performance of the model over time and update the model as new data becomes available. This ensures that model remains accurate up to date. Overall, the process of machine learning involves key steps including data collection, preprocessing, choosing an appropriate machine learning algorithm, training the model, evaluating and tuning the model, and using the model for predictions or decisions, and monitoring and updating the model over time. So here first I'll start with supervised learning. Supervised learning is a type of machine learning where the algorithm learns from the labeled data, which means that the data is already labeled with the correct output. The goal of supervised learning is to learn a mapping from inputs to outputs. There are two main types of supervised learning, regression and classification. In regression, the goal is to predict a continuous output. So here the regression examples of regression problems include price of a given house based on its features. Linear regression, decision trees, and neural networks are commonly used algorithms for regressions. In classification, the goal is to predict a categorical output such as whether an email is spam or not. Logistic regressions, decision trees, support vector machines, and neural networks are commonly used algorithms for classification. Then we have unsupervised learning. So it's a type of machine learning where the algorithm learns from unlabeled data, which means that the data is not labeled with any output. The goal of unsupervised learning is to learn the underlying structure of the data. There are two main types of unsupervised learning, clustering and dimensionality reduction. So in clustering, the goal is to group similar data points together. K-means clustering and hierarchical clustering are commonly used algorithms for clustering. In dimensionality reduction, the goal is to reduce the dimensionality of the data while preserving the important information. Also, we have principal component analysis, that is PC analysis, and SNE, also commonly used for dimensionality reduction. Then we have reinforcement learning, which is a type of machine learning again where the algorithm learns from interactions with an environment to maximize a reward signal. The goal of reinforcement learning is to learn a policy that maximizes the expected reward. The reinforcement learning process involves an agent that interacts with an environment and takes actions that affect the state of the environment. So examples of reinforcement learning applications include game playing, robotics, and autonomous driving. So these are basically main three types of machine learning, that is supervised, unsupervised, and reinforcement learning. Each type of learning has its own set of algorithms and applications. Choosing the best and appropriate machine learning depends on the problem being solved. So in machine learning, it is important to evaluate the performance of a model on a data that it has not seen during training. So the process of splitting data set into two sets, one for training the model, other for testing the model performance, is called train test split. I'm repeating again, the process of splitting the data into two sets. So one set for training the model and another for testing the model's performance is called train test split. The train test split is typically performed by randomly dividing the data set into two subsets, that is a training set and a testing set. And the training set is used to train the model, while the testing set is used to evaluate the performance of a model on a new and unseen data. The ratio of the size of training set to the size of the testing set can vary depending upon the size of the data set and complexity of the model. A common split of 80% of the data for training and 20% for testing is commonly followed. This train test split is important because it allows us to estimate how well the model will perform on new data. If we train and test the model on the same data, it may perform well on training, but it may not generalize well to new data.
So excuse me, if there are supposedly 100 samples in the data set, so which 80 will go into trainings and which 20 will go into test set?
So that was a random split. It happens with a random split. And once you have decided your train and test set, we keep them constant. We don't change them throughout the model building, evaluation, and adjustments.
So
Train
that
test split is a
randomness we decide or machine decides?
machine decides. Like it's just a random number it takes and starts splitting from that number. Like it does a random sampling. Yeah. So, but in current state, this 80-20 split or 90-10% or training of train and test data splits is mostly followed if you are generating a model for the first time. Previously no data has been reported and no machine learning model has been done, but the ideal way to develop or to increase the performance of existing models is add the new data into your training and keep the test set common. Like previously in 2020 someone might have developed a model, so they might have a train and test set, and from 2020 and 2024 you have a new data, so take that new data into your training set and keep the test set common from the study of 2020 and yours. So this will give the benchmarking studies equally. So whatever methods he has benchmarked in 2020 the methods your methods will be already performing better. So if someone has defined a test set, the constant defined test set is carried forward throughout in that study. Only the training sets and other validation sets keep on changing. So once you have defined training set and test set, need not go for train test split again. And if you are performing our if you are building our model on a new training set, we go for cross validation studies. That I'll come in next sometime.
What is validation studies in this? I mean, how do we do that?
Yeah, I'll show that when I go for Veka and all. I'll show how validation is done. Okay, just brief to give validation is, we have training set of 100 data points. So what if I train with 99 and test on one data set? What is the performance? So I remove one data point from training, train the model on 99 data points and test it on this single one what I have removed out, is called leave one out cross validation. So similarly we have leave 5 cross validation. So there are different processes. So leave one out cross validation proceeds until each data point has once appeared in the test set. So similarly we have leave 5 out, 5-fold cross validation, 10-fold cross validation, and 20-fold cross validation. Based on the number of data points, higher the number of data points, higher the cross validation fold one can use for validation of their model. So here I have a set of questions. The first one is, which type of machine learning techniques is used when a data set is not labeled? And the second one is, which machine learning technique is used when a data set has both labeled and unlabeled data? And which machine learning technique is used to perform a text classification task? Okay, so unsupervised, in unsupervised learning the data set is not labeled. So generally the data set is clustered, or the number of data points or features have been reduced under dimensionality reduction concept. So we have semi-supervised learning technique where the data has both labeled and unlabeled data. So, and finally we have supervised learning. So classification task comes under the supervised learning, where it is data sets are being labeled either as a class 1, class 2, class 3 accordingly. So here I have set of more questions again. So what is the purpose of splitting a data sets into training and testing? So whether to train the model or to evaluate the model's performance on a data it has not seen before, or to increase the size of the data set, or none of the above. What is the recommended ratio of splitting the data sets into training and test sets? Whether it is 50 is to 50, 70 is to 30, 80 is to 20, or depends on the size and complexity of the data set. And third question is, what is the difference between training set and the testing set? So the testing happens because to evaluate the model's performance on data it has not seen before. So it depends on the size and complexity of a data set. So no, there is a no defined train test split ratio, but there are some 90 is to 10 and 80 is to 20 are widely used, and that the role of training set is used to train the model and testing set is used to evaluate the model's performance. So to start with, the one of the major machine learning task is the classification. So it falls under the type of supervised learning, in which the goal is to assign each data point to a specific class or category. The input data is labeled with a set of predefined classes, and algorithm learns to predict the correct class for new unseen data based on the patterns learned from the labeled data. There are two main types of classification problems: binary classification problem and multi-class classification problems. Binary classification is a type of classification problem where there are only two possible output classes. For example, classifying whether email is spam or not. So the class is spam class, one class is spam, other class is not spam, or whether a patient has a particular disease or not. So there are various algorithms used in binary classification, including logistic regression, support vector machines, and decision trees. These algorithms are trained on the labeled data to learn patterns that differentiate between two classes. Once trained, the model can then make predictions on new and unseen data, trained and validated. Then we have multi-class classification, where there are three or more possible output classes. For example, classifying different types of animals such as cats, dogs, and birds. There are various algorithms used in multi-class classification, including logistic regression, decision trees, random forest, neural networks, and these algorithms are trained on labeled data to learn the patterns that differentiate between these classes. So in both binary and multi-class classification problems, the accuracy of the model is measured by its ability to correctly classify the input data. Common evaluation metrics used in classification include accuracy, precision, recall, and F1 score. So classification is an important problem in machine learning, with many real-world applications such as spam detection, sentiment analysis, and image recognition. In machine learning, a classification problem dataset is a collection of data that is labeled with a predefined classes or categories. The dataset is used to train a classification model to learn patterns that differentiate between the different classes so that the model can accurately predict the class of new and unseen data. A classification dataset typically consists of two main components: the input features and the target output. The input features are characteristics or attributes of each data point, while the target output is a class or category label assigned to each data point. For example, in a data set used for binary classification to distinguish between spam or non-spam emails, the input features may include the text of the email, address, time of the day the email was sent, and the target output would be the binary label indicating whether the email is spam or not. In multi-class classification dataset, the target output may consist of multiple labels to represent the different classes. For example, in a dataset used to classify different types of animals, the target output may include labels such as cat, dog, bird, etc. So these classification datasets can be created in various ways, such as manually labeling data, using web scraping to collect data, or using the pre-existing datasets available in public repositories. These datasets may be cleaned and pre-processed to remove the missing values or irrelevant features before being used for training the model. It is important to choose a high quality and representative dataset for training a classification model to ensure that the model can accurately generalize to new and unseen data. The size and quality of dataset can significantly impact the performance of the classification model. So in a classification model, the feature extraction and selection are crucial steps in the process of preparing data for training a machine learning model. Feature extraction involves converting the raw data into a set of features or attributes that can be used to train the model, while feature selection is an important process of identifying and selecting the most relevant features to improve the accuracy and efficiency of the model. So first we have feature extraction. So feature extraction is the process of transforming raw data into a set of features or attributes that can be used for training a machine learning model. The goal of feature extraction is to represent the data in a way that captures the most important characteristics or patterns that are relevant to the classification task. For example, in a text classification problem where the goal is to classify documents of either positive or negative sentiment, features may be extracted from the text by using techniques such as word frequency counts or TFID, that is term frequency and inverse document frequency scores. Then we have feature selection. Feature selection is the process of selecting the most the more the most relevant features from a larger set of features to improve the accuracy and efficiency of the machine learning model. The goal of feature selection is to reduce the dimensionality of the data while preserving the important information. So, for example, in the same text classification problem, feature selection techniques may be used to identify the most informative words or phrases that are most predictive of the class label. So, these techniques include mutual information, chi-square test, and recursive feature elimination. So, there are several types of classification algorithms in machine learning. So, the oldest one is logistic regression. So, it is a linear classification algorithm that uses a logistic function to predict the probability of a binary outcome. So, it models the relationship between the input features and the binary target variable by estimating the probability of the positive score, positive class score as a function of input features. So, logistic regression uses a cost function called the negative log likelihood, which is minimized during the training to estimate the model parameters. So, the logistic function used in logistic regression is a sigmoid function that maps any real valued input to a value between 0 and 1. The model parameters are estimated using a maximum likelihood estimation, which is involved in finding a set of parameters that maximizes the likelihood of the observed data. Then we have naive Bayes, so this is a probabilistic classification algorithm that is based on Bayes theorem. It assumes that input features are conditionally independent given the class label. So input features are conditionally independent and given the class label, so which is a naive assumption but simplifies the computation probabilities. So naive Bayes calculates the conditional probabilities of the input features given for each class label, then uses Bayes theorem to compute the posterior probability of each class for the given input features. So this naive Bayes algorithm uses the joint probability distribution of the input features and class labels to compute the posterior probability of each class given in the input features. So the conditional dependence assumption allows for the simplification of the computation of these probabilities. Then we have trees. These are the tree based methods, and they are also called as non-parametric classification algorithms that partitions the input data into a set of rectangles or boxes, each of which corresponds to a class label. These algorithms recursively partitions the input space by selecting a feature that maximizes the information gain, which measures the reduction in uncertainty and entropy of the class labels after splitting on that feature. So random forest. So random forest is an ensemble of classification algorithm, that is multiple decision trees together is called as a random forest. So now that we train a classification model and we have an output. So for example, we have two classes, positive and negative class in our training set, and model should either give an output for a as a positive or negative class. So here we have four scenarios, that is positive class correctly identified as positive, one scenario; positive negative class correctly identified as negative class, second scenario; third one, positive class wrongly identified as negative class; then we have negative class wrongly identified as positive class. So in a binary classification problem, these four scenarios exist, and this evaluation of these binary classification models is generally done using a confusion matrix. So this confusion matrix is a table that is often used to evaluate the performance of a classification model. It is also known as error matrix. It summarizes the predicted and actual values for classification problem. So in the confusion matrix, you can see we have four different terms. That is TP, that is true positives. So the predicted value is positive and its actual is positive. Then you have false positives. That means falsely predicted as positive. If it is falsely predicted as positive, then it is actually negative. Then we have false negative. So the predicted value is negative, but its actual value is positive. And we have true negatives, that is predicted value is negative and false, and its actual value is also negative. So this is how a confusion matrix is generated. So I repeat again, confusion matrix has four different metrics, that is true positives, TP shortly known. So number of instances that were correctly predicted as positives by the model and that are actually positives as well. Then we have false positives, number of instances that were predicted as positive by the model but were actually negative in reality. Then we have false negatives, number of instances that were predicted as negative by the model but were actually positive in reality. And we have true negatives, so number of instances that were correctly predicted as negative by the model and in reality also they were negative. So here I have given a example confusion matrix. So kindly mention in the chat box what are true positives, false negatives and true negatives based on the spam and not spam confusion matrix given. So I'll give about brief about this confusion matrix. So this is a binary classification problem where the goal is to predict an email is spam or not. Suppose we have a test set of 100 emails and our model predicts 60 of them has spam. Of those 60, 50 are actually spam and the remaining 10 are not spam. Also, the model predicts that 40 of them are not spam. Out of those 40, 30 are actually not spam and remaining 10 are spam. So let's restate. So here we have test set of 100 emails. So our model predicts 60 of them has positives. Of those 60, 50 are actually spam. So these 50 are true positives. Then out of 6, 10 are wrongly predicted as spam. So these are false positives, that is 10 are not spam. Then the model also predicted that 40 of them are spam. Out of those 40, 30 are actually not spam. So true negatives are 20 and the remaining 20 are false negatives. So the confusion matrix provides a valuable insights into the performance of a classification model. It can be used to calculate various performance metrics such as accuracy, precision, recall and F1 score, as well as visualize the distribution of errors made by the model. So here kindly note the orientation of rows has been changed. So here we have actual versus predicted, but this is like predicted and actual. Yeah, either ways one can represent this confusion matrix. So the first is the accuracy. Accuracy is the most basic and intuitive metric for classification. It measures the proportion of correctly classified instances among all instances in the dataset. So the accuracy formula is given as true positives plus true negatives divided by true positives plus true negatives plus false positives plus false negatives. Then precision. Precision measures the proportion of true positives among all positive instances. It is used when the goal is to minimize false positives. Then we have recall, which is also known as sensitivity, measures the proportion of true positives among all actual positive instances. It is used when the goal is to minimize false negatives. And we have F1 score. F1 score is a harmonic mean of precision and recall. It's a balanced metric that combines both precision and recall. So F1 score is given as 2 into precision into recall divided by precision plus recall. Then we have ROC curve. So ROC curve, that is receiver operating characteristic curve, is a graphical representation of true positive rate against the false positive rate for different classification thresholds. It is used to evaluate on the trade-off between the sensitivity and specificity of a binary classifier. So the ROC curve is generated by plotting true positive rate against the false positive rate of different threshold values. And you see a term called area under the curve. This is a scalar value that represents the area under the ROC curve. It provides a measure of overall performance of a classifier. So overall, choosing the appropriate classification validation matrix depends on the specific problem and the desired trade-off between precision and recall. It is important to consider the strengths and limitations of each metric and to evaluate the performance of the model using multiple metrics to obtain a comprehensive understanding of its performance. So here I have a set of questions, try to answer them. So a binary classification model has 90 true positives, 10 false positives, 5 false negatives and 895 true negatives. So the model's accuracy is, so we are solving the first one to try to calculate the accuracy. So here accuracy is true positives plus true negatives divided by sum of true positives, false negatives and true negatives. So it's 0.985. So then we have second one. A multi-class classification model has correctly classified 70 samples out of 100 samples. What is the model's accuracy? So when we consider the above formula, true positives and true negatives are the samples that are correctly classified. So similarly, we have 70 samples out of 100. So the accuracy is 0.7. And I have third one. Which of the following techniques can be used to prevent overfitting in classification models? Prevent, not versus. Prevent overfitting.
Is it cross validation?
No, all of these are used because regulation is the term that try to reduce the coefficient values to minimal. Cross validation is the one, it helps to prevent overfitting because it has data augmentation or segmentation things, and feature selection. Feature selection techniques also provides us with various metrics which helps us to prevent overfitting. So all of these steps are done in order to reduce overfitting. So next, once classification is done, we have other type is regression. Just give me a minute. So regression is a type of supervised learning problem where the goal is to predict the continuous output based on the set of input features. So continuous output means a real value prediction. In regression, the algorithm learns from labeled data to predict the value of a dependent variable based on the values of one or more independent variables. So regression is nothing but we are generating a type of equation, whether it's linear or non-linear. Why? Like output of the model has a function of different inputs. So a regression data set is a collection of data. It consists of input and output variables where the input variables are used to predict the output variable. The input variables are also called as independent variables of features, while the output variable is also called as dependent variable or target. The regression data set, similar to training, it can be divided into training data and testing data. The training data is used to train the regression models, that is generate the coefficients whether it's linear or non-linear. So regression problems involve predicting a continuous output variable based on one or more input variables. To build a regression model, it is important to select the appropriate input variables of features that are relevant to the output variable. So feature extraction and selection are two techniques used in machine learning to identify the most important features for regression problem. So here we have several methods for feature extraction. So one I missed is forward feature selection as well. But first one is principal component analysis, PCA. PCA is a technique used for feature extraction that involves reducing the dimensionality of the data by identifying the principal components that explain the most variance in the data. PCA can be used to identify the most important features in the data and reduce the computational complexity of the regression model. Next we do correlation analysis. Correlation analysis is a technique used for feature selection that involves identifying the features that are more strongly correlated to the output variable. Correlation analysis can help to identify the most relevant features and eliminate irrelevant ones. Then we have regularization. It's a technique used for feature selection that involves adding a penalty term to the regression model to discourage overfitting. Regularization can help to select most important features and prevent the overfitting to the training data. Then we have recursive feature elimination. It's a technique used for feature elimination that involves recursively removing the least important features from the dataset until the optimal subset of features is identified. So this recursive feature elimination can identify the most important features in the data and eliminate the irrelevant ones. Other one is recursive feature elimination is a top-down process. So it starts with the all features model and it keep on reducing removing the irrelevant ones and reducing the size of the feature subset. But then we have forward feature selection, so it's a bottom-up approach. So it starts with single feature, then keep on adding the features until the optimal feature subset is identified. So regression techniques are used to model the relationship between input and output variables. So there are several types of regression techniques: linear regression, multiple linear regression, polynomial regression, and support vector regression. Each of these regression techniques has its own strength and weakness, and the choice of the technique depends on specific problem at hand. It is important to evaluate the performance of each technique using appropriate metrics such as mean squared error or R squared, or to compare the performance of different techniques to select the most appropriate one. So we have validation metrics. So first one is we have mean squared error. Mean squared error is the average of the square differences between the predicted and actual values of the output variable. It is widely used in regression. So in the formula you can just consider y as actual variable and y cap as the predicted one. Then we have RMSE, that is root mean square error. So it is the square root of MSE and is also widely used. Then we have mean absolute error, MAE. So MAE is the average of the absolute differences between the predicted and actual values of the output variable. Then we have R squared. R squared is a metric that measures the proportion of the variance in the output variable that is explained by the regression model. It generally ranges from 0 to 1, where 0 indicates that the model explains none of the variance in the output variable, and 1 indicates that the model explains all of the variance in the output variable. Then we have adjusted R square, which is a modified version of R square that takes into account the number of input variables in the model. So here I have some questions. So what is the purpose of regression analysis? Whether to measure the correlation between two variables, predict the value of a dependent variable based on one or more independent variables, to identify outliers in the dataset, and to calculate the mean and standard deviation of the dataset. It is B. So to predict the value of a dependent variable based on the, so next next question is, what is the difference between simple linear regression and multiple linear regression? So it is a simple linear regression has only one independent variable, that is y equals to mx plus c or something like that. The multiple linear regression has more than one independent variable, that is y equals to a1 x1 plus a2 x2 plus a3 x3 and so on. Third one is, which of the following type of regression analysis is used for predicting the binary outcomes? Binary outcomes. So it is logistic regression, which is a binary based method. So here I have some questions before I move on to this Veka introduction. So in K means clustering, K is meant for here K defines for number of clusters. So given confusion matrix, try to calculate the sensitivity, specificity and accuracy of the following confusion matrix. So formulas I have given here. So accuracy is, first thing is very easy to calculate, true positives plus true negatives divided by true positive, false negative and true negatives. So 5 plus 1 divided by 5 plus 1 plus 4, so it will be 0.6. And sensitivity, so sensitivity formula is true positives divided by true positives plus false negatives.
Excuse me, we have to answer this in points or in percentage, because in one of the assignments they asked question was asked in percentage. So in exams, supposedly these blanks are given. So we have to answer it in percentage or decimal.
Yeah, so if only the blanks are given, it's a decimal, and if there's a percentage symbol after these blanks, so we have clearly mentioned in the questions where we want you to answer in percentage or in decimals. So if a percentage symbol is given here, we expect you to provide this in percentage, that is into 100, like 56, 100, 60, like that. So here, yeah, so here sensitivity is 1 and specificity is 0.6, just a small interchange of values. So here, let if we calculate the sensitivity, true positive value of 5, so sensitivity is true positive divided by true positive plus false negative. So true positives are 5 and falsely predicted as negative. So prediction negative, actual positive, that is 0. So 5 divided by 5 plus 0, it's 1. Sorry. And then we have specificity. Specificity is true negatives divided by true negative plus falsely predicted positive ones. True negative 1, 1 divided by 1 plus that are falsely predicted as positive but actually negative. So 1 divided 4 by 5. And we have accuracy. So accuracy is 1 plus 5 divided by 1 plus 5 plus 4. So it's 0.6. So given the specificity of a classification method has 0.75, the false positive rate will be, so here I have given the formulas for false positive rate. So it is 1 minus specificity will give to false positive rate. So 1 minus 0.75 is 0.25. So that's all for the discussion I have. Now I'll move forward to Veka. But before that, any other doubts regarding this classification or regression I could take before moving on to Veka? Okay, I'll start with Veka then. So Veka, it's Veka Environment for Knowledge Analysis is a popular open source data mining tool that provides a GA, graphical user interface, for users to apply various machine learning algorithms to their data set. It was developed at the University of Waikato in New Zealand and it is available under general public license. So Veka provides a wide range of tools and algorithms for data pre-processing, classification, regression, clustering, association, visualization. It can also be used to analyze datasets in various formats, including CSV, ARFF. RFF format is the one that is inbuilt for Weka, but Weka also takes comma separated files. The Weka GUI provides an easy to use interface for performing data analysis tasks without needing for programming. Users can load datasets into the tool and pre-process the data using filters and apply machine learning algorithms to create the predictive models and analyze the data. Weka also provides a command line interface for users who prefer to work with the tool programmatically. This interface allows users to perform data processing, classification, clustering, other tasks. Some of the popular machine learning algorithms available in Weka include naive-Bayes, decision trees, k-nearest neighbors, support vector machines, logistic regression, multi-layer perceptrons. Weka also provides a wide range of evaluation metrics for users to assess the performance of their machine learning models, including the accuracy, precision, recall measure, and ROC curve. In addition to the graphical user and command line interface, Weka also provides a Java API for developers to use the algorithms and functionality in their own Java applications. So the first thing one sees is Weka Explorer. So this is the Weka home page. Initial first page you get, then you go to Weka Explorer. So this is the Weka Explorer tab that allows users to perform various tasks related to data mining. So this Explorer contains several sub-tabs that provide access to different functionalities of the tool. So here I'll try to provide brief explanation of each sub-tab. The first one is pre-process. So this tab provides several options for data pre-processing, including data filtering, attribute selection, and data normalization. Users can apply various filters to the datasets to clean and transform the data before applying machine learning algorithms. Then next to it we have is classify tab. So this allows users to build and evaluate the classification models or regression models. Classify is just a name. So according to your output variable, whether it's nominal, that is it's a classification variable or continuous variable, the algorithms are pre-selected. So users can choose from the wide variety of classification or regression algorithms and develop and evaluate their model. Then the third one we have here is cluster tab. This tab allows users to perform cluster analysis on their data set to identify groups of similar data points. Users can choose from a variety of clustering algorithms such as k-means, hierarchical, and visualize their clusters using different visualization techniques. Then we have associate tab. This tab allows users to mine association rules in their dataset to identify patterns or relationship between different attributes. Users can choose from variety of association rule mining algorithms. Then we have select attributes tab. This tab provides several options for attribute selection and feature engineering. Users can choose from different attribute selection programs. So we have search and build attribute methods to select the most relevant features for their machine learning. Then we have visualize tab. So this allows users to visualize the data and result of their machine learning models. So to more delve into this pre-process tab, what it shows. So in that we have this sub-window, pre-process sub-window, provides a list of available filters that can be applied to a data set. Users can select filters based on the type of data pre-processing they want to perform. Then we have filter options. This sub-window, filter just below. This sub-window provides the options for configuring the selected filter. For example, users can specify number of attributes to select or the type of data transformation to apply. Then we have attribute selection. This sub-window provides options for selecting attributes based on different criteria. That is, we can select all attributes, you can select none attributes, and also you can select and remove. Then we have decretize. This sub-window provides the numeric attributes into the categorical. So this is an experimental tab. So next thing is we have been to classify tab. So here where the algorithms and options for building and evaluating classification models are performed. So we have first thing is classifier. So here all the machine learning algorithms, whether they're regression based or classification based, are listed under the name classifier in Veka. Then we have test options. So this sub window provides options for configuring and the evaluation of the classification model. So here we have different types of cross validations. So whether we need validation based on only training set, or we need a validation on a supply test set, or we need validation based on cross validation techniques based on folds, or whether one needs a train test split validation. Four different options are provided under test options. Then we have more options to see based on the results and how each individual classification task is done. And we have output predictions place. So this sub window allows users to specify whether they want to output the predictor class for each instance in the data set. So the test option sub window allows users to configure the evaluation of the classification model. Users can choose the type of evaluation method such as cross validation, holdout, percentage split, and set number of folds, percentage split, or test set accordingly. They can also specify additional options such as random seed used for evaluation, or whether or not to output the predictions or probabilities, other things. So Veka prefers to load in a RFF format. So RFF format is given here. So information, that is instant information followed by the attribute information. But with the updated Veka versions, they also accept the CSV file formats. And once you load the file, you can see the columns in your file in the pre-process tab. And also the Veka itself has defined what is the type. So it's a nominal classification problem. Veka itself recognizes based on your column what you select. So
Excuse me, what type of data sets we can use for the Veka can take into in terms of biological data sets?
like Veka can be used for any task, but make sure these columns are defined. Like it cannot generate its own features. We have to generate some numeric related features. For example, if we take a sequence length, what is the number of hydrophobic composition of hydrophobic residues, like that, and tell whether the protein is a membrane protein or a globular protein, like that. So most of the things it should be converted to numeric type or a
So I have to tell Veka ki these many hydrophobic are there, these many polar residues are there, and these many non-polar residues are there.
yeah. So Veka cannot generate its own features. We have to generate the features, and just it can only build a machine learning model.
So, for example, if I am working with a proteome data, so that it will take in terms of proteome or transcriptome data in terms of expression values.
Yeah, you can give that expression values. For example, proteome, transcriptome itself, transcriptome data and proteomic data. For each individual proteome, like if you are working with multiple organism based proteomes, each proteome you need to calculate some features that define the proteome or a transcriptome, then give those features here. For example, I'll give you an example whether to know whether set of given genes are overexpressed or underexpressed in a particular disease condition. So first we need to know what are all the genes that are overexpressed and underexpressed, and try to calculate some of the features. Like what features we can calculate from genes is composition of A, composition of T, composition of G, composition of C. So 4 columns here are generated. Followed by that, we can also generate some other features and give them as an input. So a column 1 will have whether it's a underexpressed or overexpressed. Column 2 will have composition of A. Column 3 will have composition of T, GC followed by that. So accordingly, that kind of input like CSV type inputs it will accept.
In the example that you just gave, so I have to tell ki okay, if the expression value is this much, so this is the disease condition, and if the expression value is this much, so this is the normal condition.
Yeah, we have to mention all those because the model has to train itself. So we need to give the training data set. First, we need to train the model. For that training, we need to give labels as well. That is, what is the input and what is the output. Also, we should give. Then you can use here. There is a supply test set option. In this supply test set, like you need to give training set here, open file, and you need to upload one more new supply test set. So in this supply test set, if you have any new gene which its expression condition you doesn't know, in that output label just put a question mark. All the input features you just add there, and in the output column you just put question mark. Veka will make a predictions on that question mark. This is how machine learning in general also works. Okay, I'll take any example and try to show. Just give me a minute. I have taken some conditions. So this is the Veka. So first I have selected Explorer, then open file. So this is where we input our training file. I have just downloaded some of the files. So before moving on to some biological aspect, I'll start with a basic uh, between classification and regression task. So I've taken dataset which is already given by Veka itself, which is weather nominal. So let's see what this data sets contain. So this data set has 5 columns. I think everyone can see my screen. Yeah. So it has outlook, we have temperature. So if you click on each feature, the other informations will be given here. Then we have humidity, windy, and the final thing is whether the students can play or not. One can play or not, true or false. 2 classes has been given. Okay, so we have features. What is the outlook? Sunny, overcast or rainy. Temperature also same. Humidity, whether humidity is high or normal. Next is windy, true or false, whether the weather forecast is true or false, windy. And final is the label what we need to predict, that is yes or no, whether we can play or not with these conditions. So this is a training set that is used. So once the data set is loaded, I'll go to classify, and under this click on this choose option. Under classify, choose option. So set of functions has been given. So we have base, naive base, some other updated version of base, and in functions we have logistic regression, support vector, simple logistic. Okay, I'll select the logistic regression and I'll use only training set validation here. That means the model trains on the same data and tests on the same data. Click on start. The results you have seen. Next thing is one can use cross validation since data is less. Okay, tenfold. I'll give fivefold.
If I rerun this same data set, so the values will be same or they may vary because as you said, key data set will be divided, for example, into 80 into 20, 80 training and 20 test data set.
Yeah, so here when we are using this use training set option, no train splitting of data is happening here unless you select this percentage split, which splits the data. This is only we use complete input for training and complete input for testing. In the second option, this you need to specify the external test set, like you need to upload a new test set file. In the second, in the cross validation, the instances from training, that means the data points from the training are only moved to test. For example, 100 data points you have in training. So since I used 5 at a time, so in a five-fold manner, like in a five folds, the instances in training are moved to test set, and only unless in percentage split. For example, if I mention 80 start, so now you see only 3 of them has come to training set, remaining has been used in the test set. Sorry, 3 of them has come to test set and remaining has used in the training set. Unless you specify this option, train test split won't happen in wake up.
So this percentage we are giving is for training.
Yeah, this number of instances that you consider for training. Like similarly I can make this 90 and
So
50%.
here for my question, I mean, if I rerun this with the same data set, so my this true positives, false positives will be same or they may vary
No, that's what they
for
will
the same
vary.
data set and same percentage split.
Yeah, so if you go with same percentage split, different runs, the values will vary because it's a random split happening. So in smaller data sets, you won't see much change, but if you go into larger data sets, the values will change. So why initially people also try to uh, fix their training data and test data sets. Mostly test data set will be the test data set that is widely used in existing previous studies. That is what people consider. But still, if there is no studies, one can do trial and error for the best train data set and test data set. That means you keep on doing this split for n number of times, trial and error, and try to figure out one best train and one best test set without any overlap between them, and you can keep that as a reference and do other steps. That is how others do. But if one follows this step, keep on clicking continuously, the values will change. I think I can show with the 50% data set. I think 5 to no, in these smaller data sets we don't see much change. Am I clear in this, or
Yes, for now it is clear.
so I'll take how a breast cancer. So this is a generalized breast cancer related data set. So if you observe the final stage, it is no recurrence events and recurrence events. So how come this cancer keeps on recurring, like appears in it? So we have given some set of features. One set of feature is age. Other set of features we have tumor size, menopause, uh, node related information, node caps, other information. So this is how a regression based things are done. I think this should be diabetes. So I have one more database for diabetes. So we give age again, mass, skin, insulin, how insulin they take. So this is how biological data sets are prepared. So the biological data has to be transformed into Veka understandable words to build the machine learning model. Veka only does training and building model. It doesn't understand biological context or concept. So it's the biologist or the researchers one who has to understand the concepts and provide some numerical values or some nominal values. So where Veka can understand from them and try to build the model.
Can you please share some data sets for us to practice? For example, this only diabetes one.
Yeah, I'll share them. Even some biological related ones if you have done from our previous workshops. If we have, you can use. I'll share them along with this lecture notes.
Where can we get that previous workshop data?
That is what workshop we do through NPTEL. If it is available, I'll try to send them because that is a paid workshop. But I'll try to send at least some of the practice. Uh, that's a paid workshop. What we do on Weka. So if there is any practice material available in that workshop, I'll try to send that. But these data sets and other Weka data sets also I can send. All these data sets are predefined in Weka. Even if you install Weka, you can find them. Like I'm using Mac, so you have airline data, contact lens data, CPU data. I think people can see it. Right? Glass data, hypothyroid data. There is this plant related data. All these data are preloaded in Weka. If you install Weka Workbench, all these data sets you can access. And some biological related data sets I'll try to send. Some QSI related studies or protein interaction studies, I'll try to send them.
Okay, so you'll send along with the recording of
Yeah,
this web.
yeah, I'll do along with the PDF of this.
Okay, thank you.
Or tomorrow I have a class. If not, I can show those data sets. If at all I have some restrictions in sharing them, I'll try to display them in tomorrow's class and show this Weka how we generate those features and how we use Weka for generating model as a live demo in the class. At least I'll try to do that if I'm unable to share those.
Tomorrow's class is at 5 to 7, right?
Yeah, it's 5 to 7. I thought I'll take a recap of all the numerical problems that I have done till now. But I can take 10-20 minutes for those data sets and finish off those.
Okay, thank you.
So this is about Weka Workbench and machine learning. So this is the last problem solving session that we have. Next session will be on recap, that is tomorrow 5 to 7. So if any other questions regarding this or anything you want me to show tomorrow, so I'll get prepared. So do let me know. I'll be in the call for some time. Yeah, even for practice purpose, one can simply generate. Open your Microsoft. People can open their Microsoft Excel. Open any blank workbook. Make it as class feature 1, feature 2, feature 3, feature 4. So class you can put A class, B, some random data. One can generate features, could be any random numbers like 2, 5, 7, 3, 5, 6, 4. So here other features can also be nominal, yes, no. can also give higher numbers like 100, 200. Let me fill this. So one can generate their own features like this and also give input to Veka and try their own. Just this is a practice purpose. This is a random model. It won't make any actual sense, but to practice to how to handle data, this is the best way. I'll also share those data sets. So any other questions other than this? Tomorrow I'll surely try to share the data sets or at least show them here. Yeah, if no other questions, you people are free to leave. Yeah, thanks for joining.
Vika is online version also, or only we can download and use it.
Yeah, we have to download. It's an installable version. Installation is required, but it has for all Mac, Linux, and Windows. Everything it supports.
Okay, okay. Then see you tomorrow then at 5 p.m. Right?
Yeah, 5 p.m.
Thank you.